Proto Labs. Real parts, really fast. Custom metal, plastic, and liquid silicone rubber parts in as fast as 1 day.
Dongping, that was badass, dude. So good job on being the first. Now you set the tone for the rest of us to follow. I wanted to get a little bit of the demographics in the room, because I've been looking forward to this for a long time. So there's some questions that have been banging around in my head, and I think that this might be the right kind of audience to give some feedback on that. How many of you guys are industrial designers? Majority. Architects? Wow, there's only a couple. You're a minority here, man. And how many of you are user experience, web design, graphic design? Not that those should all be thrown together, but for the sake, okay. So mostly industrial designers here. And I will say, being trained as an architect, and Dongping, I'm sure you can concur that I'm really envious of the industrial designers, because typically what you're designing is something that you yourself can create. You don't have to align political forces and appeal to the mayor and get a bunch of funding and all this other stuff in order to build it. Obviously, if you want to democratize and give everyone access, it's a different story. But the ability to actually design and make your own thing, I was always envious of. A little bit more background for myself. I was, like I said, I went to school to be an architect. I've actually worked in manufacturing and aerospace, and then a stint as a tech entrepreneur, and that's what brought me to Autodesk, where I'm now a technology futurist. And more on that later. I'm sure many people are like, what the hell does a futurist do? I'm still figuring that one out, by the way, so the verdict's still out on that one. But one of the topics that I'm focusing on is machines and machine learning and how we can teach machines to design. And I think that there's an interesting trend happening now in design, and it's like an amazing time for all of you in the room to be a designer, because the world's asking for it in all places. For pools that we need to put into our river, to housing, to new products, to sustainability, all these issues are coming together, and designers are in the position to solve a lot of those problems. And I think that there's certain trends that are happening now that are unifying the disciplines of design. I've never really looked at architecture, product design, user experience design as separate disciplines, and I think that there's a lot of convergence that's starting to happen, and actually some of these technologies we'll be talking about today I think are accelerating that trend. So starting off, I'm going to get the graphs out first, and then we'll just get to pretty pictures thereafter. This is actually data from when I was part of a startup before we were acquired by Autodesk, and one of our clients came to us and said, hey, we found some really interesting stuff using your software. So the software is called Glue, and it's basically a web collaboration software for 3D. Okay, so imagine GoTo meeting with 3D capabilities. So all the different designers, all disciplines, could be in the same three-dimensional space at the same time and coordinate their designs. So obviously, this was focused on building design. And this was a team building a theme park. So you had the structural engineers and the architects and the electricians and the ride and show people, lots of different groups. And traditionally, it's very hard for them to collaborate. And this was kind of pre-cloud era. Our startup started in about 2008. So this was new at that time. And after they had deployed the software and were using it for a while, they started noticing a trend that they would update their designs much more frequently. So what you're seeing in the graph, the gray is their design iterations pre-cloud, and then the orange post-cloud. And this is a weekly, each of these columns represents a week during that project. So what you can see very, very readily is that they quickly started iterating. And it shows you that given the opportunity to iterate designs, designers will take advantage of that, right? And a couple of orders of magnitude more design iterations at the end of the project than they would have previously done. So that's interesting. So you're thinking all these people together, given the opportunity, want to go through more designs more quickly and evaluate all of those. And I was thinking, well, is that unique to this industry of buildings? These are obviously really big, complex systems. This is like just HVAC and plumbing and mechanical for building design. This doesn't even have the architecture in it. And I was like, is this unique to that industry, or is this a case for all designers in all industries? And I think most of you can attest that given the opportunity, you would want to design as much as possible. And basically, you're trying to converge on a solution. You're trying to optimize that design. And I think that applies whether you're doing buildings, you're designing a car, you're doing character illustrations or sketching. That's something that we all go through. You never get it right the first time around. Even I was talking last night to Sarah, who's working on a musical. Again, they're designing this performance art, and they go through a lot of iterations with a team, and that collaborative capability is a key component of it. So it gets you thinking, if we're going through all these iterations, why are we doing all the iterating? Meaning, we know what we're trying to get to, we know what we're trending towards. How can we find another way to go through those iterations more quickly? And this is where algorithmic design, computational design, we often internally at Autodesk call it goal-driven design. That's where it comes into play. So what you're seeing here is an example of a project that we have called Dreamcatcher. And the idea is, you have your dream, you have your goal, and let's figure out how to catch that goal. And this is a bracket. This is actually a lunar lander from Moon Express. These guys are sending this lander to the moon next year. Now, that alone is pretty badass, actually. The fact that we're in a society now where, hey, I want to send something to the moon. I'll do it. It's going to ride on a SpaceX rocket. It's going to launch, and I think it's slated for like the second quarter next year. So these guys needed a bracket to hold this thruster. So what you're seeing here is a thruster that has 5 degrees of freedom, right? So it can rotate in multiple directions. So there's a lot of different loads that happen on this bracket. It's not just pushing up. And they wanted to make it as lightweight as possible. Obviously, payload is really expensive to send into space. And they came to us and said, hey, do you think that you could do something to optimize this design? And so we put it through, and this is still research phase technology, but we put it through the software, and this is ultimately the design the software came up with. Now you look at that, and that's not intuitively probably what most designers would come up with. And by the way, even if you did, you probably wouldn't want to sit down and draw that thing, or the 10,000 iterations of this thing that happened before the optimum was found. So what the situation is, basically the designer is setting up the constraints of the problem, right? Becomes the domain expert. Just like I don't think you probably plan on being a domain expert in pools and water filtration, but you learn the expertise. It is the information age. You understand the problem, you constrain the problem, and set the parameters by which it's going to grow. And that's exactly how this solution came about. Is really grown. So in this video, you can see what we call the Trellis Growth. This is the way it's seeded and germinated, and it's using genetic algorithms to create this branching structure. Now, this is slowed down for human comfort. This actually, we go through this iteration in about 1/3 of a second. So each one of these is grown, and then it's analyzed. So we go through finite element analysis, figure out what its stresses and strains are, and go through another iteration. So if you're doing 3 of these a second, you can imagine that you do quite a few of them pretty quickly, especially because this is all being computed, again, in the cloud. So the cloud is the enabler of that collaboration. The cloud is the enabler of the computing power necessary to drive through potentially billions of iterations of synthetic evolution. What's also interesting is the way, and I'm not going to geek out too much, but the way we're representing this geometrically is also conducive to the analysis. Because one thing that we found out in one of the first iterations, that when we had this crazy structure, and we went to analyze it, translating, and for anyone who's done any kind of finite element analysis or simulation or optimization, translating it from your design model into the analysis model can be a pain in the ass. So this is actually generated, the geometry that's used to represent it is the same geometry that's used to analyze it. So the two are mutually inclusive, because the first time we did it, we found out that the amount of computing power to translate it was actually more than generating the form itself. So that's another step that we've taken to optimize that. And now this is starting to be discussed. Fast Company ran this article recently. I cross out, it's a great article, but the title is a little bit misleading, like algorithms are the next star designers. The algorithm isn't designing. The designer is still in control of this process, but essentially the designer is now getting the power to go through all those iterations without manually doing it. And if you take a step back, and obviously with Autodesk coming from the CAD world, and our CEO often says that computer-aided design was really a misnomer because it wasn't aiding you in doing anything. It was just documenting. It was like computer-documented design. You have the design in your head. You draw it out. It's nice to have a computer to help you do that, to help you simulate it. But at the end of the day, it's not really helping you achieve that design solution. This is actually now aiding you in achieving that solution. So in this case, this is actually David Benjamin, whom some of you may know of The Living, also teaches at Columbia here in the city. And he was using this technology to iterate the designs for this chair and went through tens of thousands of iterations. And this is essentially the ranking Some of you guys may know this PMP type of graph, but these are basically all the different parameters that you're trying to optimize for. And sometimes when you're optimizing for one, you're sub-optimizing the other, right? It's a trade-off. It's multidisciplinary optimization. And this was the end result. So you think of the standard concept of chair as an object, and then a pseudo-optimize where you might mesh that chair to make it lighter, use fewer materials, it's easier to carry around, still maintaining all the structural properties that a chair needs. And then the ultimate where we retrieve about 3 times weight reduction by creating this optimized lattice structure. And what's interesting is this could be optimized for every occupant of that chair. You just define how high you want to sit, how far you want to lean back, how much you weigh. You have to be honest, and it'll give you a solution. Now that's a pretty simplified problem as a chair, right? But the results are quite intriguing. So what happens when you start putting in more constraints? And aerospace and other industries have been doing this for a while, but the thing is really genetic algorithms are a great way at finding tens of thousands of bad ideas really quickly. I mean, they're stupid, right? A genetic algorithm does not know what the solution is. It's just trying and searching a broad solution space, and it's really like taking a big-ass shotgun and taking 1 billion shots in the dark. So how do we make it more intelligent, right? And genetic algorithms have been used for a greater part of a decade in experimentation in the design space. And they're very efficient at searching large areas, but they're not great at achieving necessarily the solution that you're looking for. So this is where we're going from here. We have a lot of work going on in the biotechnology and synthetic biology world, where we're simulating the self-assembly of matter. So you think about, you yourself are a great example of an assembly machine, and using your DNA as a seed to instruct particles of how to come together. And basically, we're creating that software to simulate these systems and figure out how they self-assemble and what that genome is for the design. Okay, so there's a lot of lessons learned here. We're working with the Wyss Institute at Harvard on designing drugs and basically figuring out how to assemble molecules that can do targeted attacks on cancer and other diseases. So with this learning, we're getting into how can we actually make these searches more intelligent. Okay, so instead of just searching a huge space of all possible geometric variations, how do we target that search? Now there's examples in other industries, and you can't have a good presentation without cute pictures of cats. And GIF making is way too easy now, so sometimes I go a little bit too far on the GIFs. But Google has done amazing things in the image search space. And I don't know if you guys saw a couple of months ago, they had an announcement about their machine learning algorithms that they're using to identify images so that it could search and find cat, or it could search and find paper shredder. And what they're doing is not telling it what a cat should look like or what a paper shredder should look like or a chair. They're just feeding it a bunch of images, millions and millions of images, and having the machine figure out what is significant in that picture or which multiple objects are significant. And the somewhat scary part is the fact that this algorithm has developed itself to a degree at which the original developers can't tell you how or why it's performing as well as it is. So it's finding cat in images, and they actually reverse engineer the code to figure out how the algorithm identified cat. It's a little scary, but it's also some amazing possibilities there. Now again, we're just searching pixels here, right? So think about what would happen if you searched 3-dimensional space and could find objects. Now, it's a cubic function more difficult because it's not a squared, it's to the 3rd power. But these technologies are starting to evolve. And in fact, one of the examples that the lead engineer gave was of a paper shredder, and he said that it was actually better at identifying brands of paper shredders than a human was. There are certain subtleties that humans wouldn't notice. There's other industries that are doing this. Here close to home on Wall Street, you guys probably read a lot about algorithmic trading and the trading wars that have been going on for a couple of decades. Similarly here, the original developers, if they were to look at their highly recursive algorithm that has developed itself over trading and performance data for over a year, they can't recognize that code anymore, right? So the person who sat down and wrote the algorithm to teach itself to change based on its performance, they don't recognize the outcome. So again, these things are starting to perform at levels beyond which we ourselves can perform, first of all, but also which we're starting to get to the point that we don't understand it anymore. Architects is way overused. Does anyone else concur with that? That word gets thrown around all the time. So this is some other research we're doing now. So we talked about the evolutionary design and going through using genetic algorithms to search large solution spaces. Now, how do we add intelligence? So this is a Design Graph Explorer, and this is basically searching geometries and finding, imagine you did a design of a building or you did a design of a chair, it can search all the components in your 3D model and identify those components based on nothing other than geometry. So no tagging that this is a bracket, no tagging that this is a piece of structure. It actually goes through and searches. So what it's doing is this is a list of projects ranging from an excavator to a bicycle to a building. And here it's found all the instances of an elbow, of a hollow tube elbow that were used in this. So this could be a huge elbow, it could be a small elbow, it could be for conduit, it could be for an exhaust pipe. It doesn't know the difference, but it does know all those instances of elbow. And the point here is that we collectively, as designers, over the last few centuries, over the last few thousand years, have been converging on solutions to problems that we have. But why do we have to reinvent some of those solutions every time? How can you find the solutions that you yourself have already used, your team has already used, or the broader human race has already used to achieve a design solution? And can we start leveraging this intelligence to drive the algorithms to achieve better solutions more quickly, rather than searching out all the dumb stuff? So here it found this example of elbow, which is on an exhaust stack on this specific excavator. So imagine you feed it in all the 3D models that you've ever created, all the 3D models that everyone's ever created, and it starts parsing all of that, indexing it just like Google is indexing the web. All right, so this is kind of the next generation of the three-dimensional web. Now, what's interesting now with products like Fusion, which is cloud-based, so you have inherent collaboration, right? So you have lots of people, big community here, all creating solutions. Okay, so that gives you great, you have the big data part. And it's very easy to sculpt and create designs with. It's called a direct modeling technique. And it's coupled with the mechanical design, right? So you can do all the form finding and shaping, and then you can do all the mechanical design, connections, electrical design embedded in there. And it does the simulation and the manufacturing, right? So you kind of have that all-in-one in a cloud solution. And when you see this community engage, you're benefited with the fact that you have a lot of people finding design solutions. But the challenge is, if you look at the diversity of solutions here, we've got Tanner's beautiful alarm clock, you've got a lamp, you've got a car. So it's hard to start to codify this if you're going to teach a machine how to use it, right? If you focus on a discipline, let's say you're doing a building, it's a little bit easier to start to index all that information. So this is the challenge, right? We've got the benefit of now we have this data, and we're seeing how people design and seeing how people converge on a solution, but very long ways from figuring out how to generalize that idea. So now shifting gears a little bit, but to talk about the trends in this industry and where we as a company have traditionally been, obviously in the software space. But as you all know, in a design project, you're learning about all the materials, right? You're learning about the hardware. You can't separate these things anymore. All these, the software, the hardware, the material side are conflating, and especially when you look at technologies like additive manufacturing, 3D printing, right? It's very hard to develop one of those things without pushing the envelope of the others. So that's why you guys may have seen that we announced the Spark platform and our own 3D printer. And the intent here is to have this as an open platform that everyone can develop on top of. The BBC analogy to Android is not inept, actually. It's a pretty good analogy of having an open platform where we've already solved a lot of the solutions and design challenges around 3D printing. What orientation does the thing need to be? How are you going to support it? All those little design considerations are taken care of, and now you have this platform that you can develop new hardware on top of, new 3D printers, new materials, and new software applications. And the printer itself, by the way, is also we're going to publish the blueprints of it so that people can hack and modify this thing, is the intent going forward. But it shows that it's very hard to just focus on the design software without getting involved in how the thing is actually made. The two are mutually inclusive. Now, looking down the path in additive and kind of pulling this into the context of teaching our machines to design, what's really exciting now is there are major equipment manufacturers. People have been making CNC machines and water jet cutters and robotics for the last 50 years. They haven't just been sitting on the sidelines watching the 3D printing companies take off. They've been looking and seeing what are the compelling technologies that they can leverage and put in their production machines, right? And these are the guys that know how to build big stuff, high precision, high repeatability, high quality. So this is from DMG Mori. Mori Seiki builds CNC machines, and this is a laser cladding technology. So it's basically 3D printing metal. It's a metal powder. It sprays it on, and it fuses it on contact with laser energy. It also combines it, though, with traditional CNC machining. So now you can print the thing and machine it, because you're not going to get the accuracy. If you go and look at this swing arm that's in our exhibit back there, you're going to see a 3D printed part with machine parts. When I went to fit the machine parts onto the 3D printed part, they didn't fit because there's the tolerance disparities. So combining the two into one is a very good idea. So now basically there's just a 3D printer head on an existing CNC machine. And the other thing to note is that we've always been obsessed with this idea of the 3D printer that can print everything. And the reality is the first industrial revolution taught us that there's a place for purpose-built machines, right? The machine that makes a turbine blade is going to be very different from the machine that's printing tchotchkes on your desktop. You know, it's a scale issue, it's a material issue, it's all these things. So you'll see the emergence of these bespoke 3D printers that are built for a single purpose. I could watch this thing over and over. I love these machines, but these are actually out on the market now. And there's 3 other manufacturers that have combined additive subtractive machines. Now, the reason I bring this up to this community is that the applications for this are immense. The things that we can design that we've never designed before. And I've been talking to a lot of big engineering firms, like think of big aerospace companies and the leads of engineering and design at these places. And they are so desperate to get people in who do not have the limitations of their traditional design engineers, right? The people they get in are thinking about fillets and bosses and draft angles and all the stuff that you learn in traditional manufacturing. And that's great for traditional manufacturing. But now they have to wipe that slate clean. It's really hard to untrain people, especially if you've been indoctrinated in an engineering program. And so they are desperate for this. One of these guys said that his best engineer, his best designer, came from automotive design, body styling. The guy was purely surfaces, body styling, clay sculpting, and he is the one has been able to leverage, and you see that 3D printed fuel nozzle that G is using? That guy was a key role in making that happen. So that's why I'm appealing to this community, is that there's broader applications here for the talents that you guys have cultivated. And I think to truly take advantage of what the additive technologies can do, it's going to have to leverage algorithmic design. As a human, we're literally not going to be able to draw all the detail necessary to push the limits of what these machines can do. So the kind of final appeal here is that really the algorithmic design will enable you guys to do what you do better. It'll allow you to go through more iterations, to optimize your design, to take advantage of additive manufacturing and 3D printing. But to be honest, you guys aren't the ones that I'm worried about. I'm not worried about necessarily this scene that you see on the page here. What I'm worried about is the shit. What I'm worried about are the strip malls and the slums and the really nasty car designs and the really ugly chairs. Most of the world that we live in is not designed. Or if it was like a leftover at the end of dinner. This is the stuff I'm worried about, and this is where I think actually algorithmic design could have the biggest impact. Because even if you can improve the energy efficiency and even the beauty of a strip mall, every strip mall on the planet by 5%, you've had a much bigger impact than improving BMW's new car by 1%. Now, it may not be as sexy, but this is why automation can go a long ways in these spaces, right? To touch all the things that aren't designed. I mean, 8% of the world's buildings are actually designed by an architect. The other 92%, it's developers, it's contractors, it's, I don't know, they found a drawing somewhere and they built it. 92% is not designed by an architect. Now, I don't know what that number is in industrial design. Obviously, there's somebody somewhere who's sending a drawing to the manufacturer. But as we all know, most things are not designed that well. So hopefully, you guys can find a way to start working in at least the thoughts on where algorithmic design might fit into your process, and then how we can start applying it to the world that isn't designed now. Thank you very much.